Have you ever actually thought about what happens the exact second after you swallow a pill? I mean, we usually just wait for the headache to vanish or the infection to clear up, right? But inside, there is this epic, high-stakes battle going on. In today's Explainer, we're going to unpack the hidden mechanics of how our organs relentlessly identify, process, and eventually flush out the medicines we take. Let's get right into it. So, to really understand this internal battleground, we first need to define our terms. We're talking about pharmacokinetics, which literally translates to drug movement. And hey, it's super important to distinguish this right out of the gate from pharmacodynamics. Pharmacodynamics is what the drug does to your body, like lowering your blood pressure. But pharmacokinetics, that's the whole story of what your body does to the drug. The absorption, distribution, metabolism, and excretion. The whole shebang. Okay, so here's the foundational rule of pharmacokinetics. Your body literally sees drugs as foreign invaders. Its immediate number one goal, get them out. We tend to think of our liver and kidneys as just simple filters, but no, they are our frontline defensive organs. The second you swallow a pill, it travels from your gut straight to your liver for something called first-pass metabolism. The liver gets the very first crack at destroying this alien chemical before it ever hits the rest of your bloodstream. It doesn't know the difference between a life-saving antibiotic and a poisonous plant. It just detects a strange chemical and works overtime to kick it out of your system. So how exactly does the liver mount this massive defense? It uses a really clever two-phase attack. See, here's the problem. Most drugs are designed to be lipid-soluble or fat-soluble, so they can slip right through our cell membranes. But to flush a drug out in your urine, it absolutely has to be water-soluble. Enter step 1, phase 1 metabolism. The liver uses processes like oxidation, reduction, and hydrolysis, heavily relying on these things called cytochrome P450 enzymes to make the drug more polar. Then comes step 2, phase 2 conjugation. The liver basically couples the drug with endogenous molecules, like glucuronate or sulfate, making it completely inert, highly water-soluble, and perfectly prepped for the exit. Now, what's really interesting here is the math behind how fast this metabolism actually happens. It's divided into two types of kinetics. First-order kinetics is how the vast majority of drugs work. Basically, the elimination rate is directly proportional to the amount of drug in your blood. If you have more of the drug in your system, your body eliminates it faster. Simple, right? But zero-order kinetics is a totally different beast. Here, elimination happens at a constant, fixed rate, completely independent of the plasma concentration. Your body can only process a set amount per hour, no matter how much is floating around in your system. To show you exactly why knowing the difference between those two math models is so incredibly crucial, let's look at a real-world scenario. We've got a bit of a medical and legal mystery here. A 27-year-old woman is celebrating the new year. She drinks heavily, about 30 units of alcohol, and finishes up at 8 a.m. It's now 10 a.m., and she wants to drive home. Is she legally able to get behind the wheel? Let's do the clinical math. The answer lies in the number 26, and here's exactly why. Alcohol is metabolized via zero-order kinetics. Her liver processes it at a constant, fixed rate of roughly 1 unit per hour. Period. She consumed 30 units. Now, the legal driving limit in places like the UK is roughly equivalent to 4 units remaining in the blood. So 30 minus those 4 allowable units leaves 26 units that absolutely must be metabolized before she's legal. At 1 unit an hour, that takes 26 hours. Since it's only been 14 hours since she started drinking, she is wildly over the limit. It just goes to show how dangerously slow zero-order elimination can really be. Okay, now let's flip back and see how this builds our understanding of standard medications, which, remember, mostly follow first-order kinetics. For these drugs, we measure elimination using plasma half-life, usually written as T1/2. This is the exact amount of time it takes for the concentration of a drug in your blood plasma to drop by exactly 50%. Because your liver and kidneys are metabolizing and eliminating the drug at a rate directly proportional to its concentration, this half-life remains a constant time interval for that specific drug. So what does this all mean for patient care? Well, the golden clinical rule of thumb is that it generally takes 4 to 5 half-lives to completely clear a drug from the body, or on the flip side, to build it up to a steady therapeutic state. This biological math dictates literally everything about prescriptions. It's the exact reason why a blood pressure medication like Ramiprela, which has a half-life of 13 to 15 hours, only needs to be taken once a day. But something like morphine, with a short half-life of just 3 to 4 hours, you have to give that 4 times a day just to maintain a steady state of pain relief.
All right, let's look at another medical puzzle that highlights a huge, massive danger in how drugs are metabolized. Picture a 63-year-old man taking a steady, safe daily dose of warfarin, which is a blood thinner. He gets a chest infection, and his doctor prescribes an antibiotic called erythromycin. But within days, he's rushed to the hospital with severe bruising on his flanks, and his blood is dangerously thin. His INR is 8.5. For context, the safe range is just 2 to 4. So what on earth went wrong here?
The culprit is a completely invisible collision happening right inside the cytochrome P450, or CYP, enzyme system in his liver. See, many drugs are substrates, meaning they're metabolized by these specific CYP enzymes. But some drugs, like that antibiotic erythromycin, are CYP inhibitors. They actively block the enzymes from working. So when the antibiotic blocked the enzymes, the liver literally stopped metabolizing the warfarin. The blood thinner just built up to toxic levels, causing dangerous internal bleeding. On the flip side of this, some drugs are inducers, like rifampicin. These speed up the enzymes, causing the body to chew through co-prescribed medications way too fast, basically rendering them useless. It's a ridiculously delicate chemical balancing act.
Let's shift to our final and honestly perhaps most dangerous clinical case. A 24-year-old man arrives at the clinic after a bad breakup. He admits to taking 40 paracetamol pills about 6 hours ago. But here is the terrifying part. Right now, he looks entirely well. He's sitting up, he's talking, and these initial blood labs actually look completely normal. No red flags. So why is the medical team treating this as a massive, high-stakes emergency? Because what's happening invisibly inside his liver is a silent, ticking clock.
To understand why, let's first look at normal, healthy paracetamol metabolism. Under a normal dose, 99% of the drug is sent right down that safe phase 2 conjugation pathway we talked about earlier. It gets bound up to glucuronide and sulfate and is easily flushed out in the urine. But about 1% gets metabolized down a totally different pathway into a highly toxic byproduct called NAPQI. Thankfully, our liver has a built-in defense for this too. It uses a substance called glutathione to quickly neutralize that toxic NAPQI before it can cause any harm. But look at what happens during a massive overdose. Those safe phase 2 conjugation pathways, they become completely saturated. The liver literally runs out of the molecules it needs to make the drug safe. Because all the safe doors are locked, massive amounts of the drug are forced down that dangerous pathway, creating a huge spike in toxic NAPQ. This rapidly burns through the liver's emergency stash of glutathione. And once that glutathione is gone, the NAPQ starts destroying the liver cells themselves. That is exactly why it's a ticking clock. Medical teams have to urgently give an antidote called N-acetylcysteine, which chemically replenishes the glutathione and mops up the excess toxin before irreversible organ failure sets in. Now, assuming our liver has successfully survived the onslaught and made the drugs water-soluble, we finally reached the last stage of our biological journey, renal elimination. The kidneys act as the ultimate exit doors, and let me tell you, they have strict bouncers. Glomerular filtration simply strains the blood, allowing smaller drug molecules, we're talking those with a molecular weight under 20,000, to pass straight into the urine. For other drugs, the kidneys use active secretion. They use specific anion and cation transporters to physically pump the drugs out of the blood. But here's the real kicker, and exactly why the liver's job was absolutely crucial. If a drug is still lipid-soluble, it will passively diffuse right back into the bloodstream through the kidney tubule walls. The body simply can't let it go unless the liver did its job first. From the incredible chemical engineering of the liver's cytochrome P450 system to the strict mechanical filtration of the kidneys, we've seen just how aggressively our bodies fight to maintain chemical purity. It is an absolutely amazing biological defense system, but one that constantly complicates how we treat disease. It leaves us with a fascinating question. If our bodies evolved to relentlessly seek out and expel foreign substances, how might the medicines of the future have to outsmart our own biological defenses to save our lives? Thanks for exploring this with me in today's Explainer. Until next time, keep questioning the hidden mechanics of the world around you.